Hey, this is Brock Lemires, and in this video I'm going to continue talking about AC signals, and I'm going to introduce a critical component to our electrical power grid, which is the transformer. Okay, so back in the 1800s, there was a scientist named Michael Faraday, and he was studying the interaction between electricity and magnetic fields. And a lot of his discoveries are kind of lumped under this thing called the Faraday's Law of induction. But he actually came up with multiple things that are really amazing and that we use today, specifically within our power grid. So, Michael Faraday, if you recall from prior videos, he was the one that discovered that if you move a charge through a magnetic field, the charge will experience a force. And so what engineers did, it says, well, hey, I can put charge through a magnetic field in the form of a wire and an electron moving, and that wire will then move. And so we started building an electric generator. One of the other things that he found, though, was this notion of induction, okay? And what this means is, or what the experiment was, is he had this thing that was called this iron ring apparatus. And he took this ring, and it was like iron, coated iron, right? So it wasn't conductive to the outside, but it was made out of iron. And he wrapped a coil of wires around it. And then what he did is he flipped a switch and started driving current through it. And he noted, this is, in theory, this is an AC signal, right? Because there's no current flowing. Then he turns it on, current starts flowing, gets really high, and then he would turn it off. So he was kind of able to do an AC signal by turn it on, turn it off, turn it off, turn it on, turn it off. And what he discovered was that if you had another coil of wires that was wrapped around that same iron ring, you would actually see an AC signal over here. And so somehow there was current and voltage that was being induced in this secondary coil by driving current and voltage, or driving current through a primary coil. And that then became what we call the transformer. And so this is an amazing thing where you have coils of wires that are magnetically coupled. So the magnetic field lines couple between these two coils of wires. And this was the big discovery that Michael Faraday made, is if you run an AC signal through a coil of wires, it will create a magnetic field that if you are close to another coil of wires, it will actually couple onto that coil of wires and cause current to flow. So you drive current into one coil, magnetic field lines, or what we call magnetic flux, is created that is then coupled onto a secondary coil, and then that coupling actually causes current to flow in the secondary. And these are not touching. Okay, now this iron core that sits right here, it just improves the strength of this magnetic flux, or this kind of field, B field or magnetic field between these two. And so you don't technically have to have that, but it makes it way, way stronger, okay? Okay, so it's this is awesome. Well, this is called the transformer. And what's really important about the transformer is that it doesn't work on DC signals. It only works on AC signals. All right, so you have to be alternating current back and forth, back and forth. If you just put DC through this, it doesn't work. And this turns out to be one of the key components to today's AC power grid, because we are allowed, it enables us to basically have an AC signal that comes from a generator, and we can use this coupling through a transformer, and depending on the number of coils that we have in the secondary versus the primary, we can actually step the voltage up or step the voltage down in order to get the voltage that we want. Okay, so this transformer has a symbol that looks like this. So you have your AC signal source, your AC source, of course, it has to be AC, and we'll call this 1, okay? And then what it's going to do is it's going to come through in a transformer, and what we do is we draw it like this, where you have coils of wires, and it's pretty descriptive, okay? And then you're going to have some load resistor over here, so we'll call it R load. And what we do is you tend to draw lines in between them so to represent the coupling. And kind of the syntax is, or the format is, if you do 3 lines, that's called an ideal transformer. If you do less than 3, then it's not ideal. And we'll talk about that in a second, okay? So this is amazing, because if you think about the first circuit, you're going to have some current that flows, and we'll call it I1. And then you're going to have some current over here that is induced, which is I2. And then that is you're going to have some voltage here, which is V2. So you have V1 and I1, and then I2 and V2. And it turns out that the magnitude of these quantities over here on the secondary side, or the load side, have to do with what we call the turn ratio of the transformer. So if you come along, we define N1 as the number of turns in the primary. Okay, and so you say, what is the primary? Well, the primary is where is the side of the transformer that's being driven. Okay, so this has the AC source that's providing power into here. It's driving current in, it's putting a voltage across it. It's basically delivering power into this side of the transformer. So that's the primary. And the number of turns is basically how many coils you have through here. And then if you come over here, you're going to have N2, which is going to be, as you can guess it, the number of turns in the secondary. Okay, and so what is the secondary? Well, the secondary is what receives the coupling. Okay, and so this is, you can think of it as the load side of the transformer. Now, it turns out what's pretty amazing is that we define this thing called the turn ratio, which is a lowercase n, and this is going to be the turn ratio, and it is defined as this: n is equal to n2 over n1. Okay, and so it basically is a ratio of the turns that exist within this transformer. And here is where it really gets neat. You can actually write out the current and the voltage that you will see on the load side using these equations. So you can say that V2, let me put it as V2, is going to be equal to N multiplied by V1. So the voltage that you see over here is actually multiplied by the turn ratio. And then I1 is actually going to be, or excuse me, I2 is actually going to be I1 divided by N. And it's like, wow, okay, so this is cool. One of the things that's really interesting is that you immediately notice that it's like, well, okay, so if I had V1 and I1 and I relate it to I2 and V2, one of the things is V goes up, or excuse me, V2 goes up as you go through the transformer, and I2 goes down. All right, so if you think about it, if N is equal to 1, then it's just 100%. So it's like the voltage V1 is equal to V2, I1 is equal to I2. But what would happen if you had N is equal to 2? Okay, well, V2 would actually be twice V1, and I2 would be 1/2 of I1. And so you can kind of notice this pattern where really what is important with a transformer is this: the power over in 1 is equal to the power in 2. And if you think about that, that gives us this amazing ability to say that P1 is equal to P2, and that is I1 times V1 is equal to I2 times V2. And if I wanted to keep that equation working, which we do, this turn ratio equation allows us to do something like this. I could actually step up the voltage as long as I step down the current, and the transformer would still maintain. The transformer operation is as expected. And so look at that. I can actually create different turn ratios, and I can say, you know what, instead of sending out like, 120 volts, I want to send out like 100,000 volts. But I also have to take the current and go way, way down. And so it turns out that this becomes very advantageous when we look at the AC power grid, because a lot of times what we do is we want to step up the voltage and then step down the voltage. So we want to take generation and we want to step it way up as we transmit it, and then as we get near cities we want to step it down, and then when we get to a house we want to step it down even further in order to make it safe. And so we use transformers all over the place in order to handle this stepping up and stepping down of our AC power grid. Okay, so let's do an example using the equations that we now have. So we have the turn ratio, we have the relationship between V2 and I2 based on V1 and I1, and the turn ratio. And we also have this thing that the power between the primary side and the secondary side is equal, so you conserve the power. Okay, so let's just say that we had a circuit that was AC, and you had plus and minus, and let's just say you had 1 volt AC. Okay, so you have 1 volt AC, and then you go through a transformer, and you have, I'm going to drop where you have a whole bunch more current coils on the load side, and we're going to put that through some resistor. And what I'm really curious about is I just want to know, I want to look at this turn ratio and figure out how it impacts the current. So we're going to have I1, and let's say that that's 1 amp. Okay, and so we have 1 volt and 1 amp over here, and it goes through here and it couples, and then what happens is that you have some I2 and some V2 that sit over here that's based on the turn ratio. So let's say that we just had N2 is equal to, let's do like 100, okay, and then we'll do N1 was equal to 10. Okay, so we have 10 turns over here and 100 turns over here, and I want to see what I2 and V2 are, and then I want to figure out if the power is preserved, and we'll just double check our work. Okay, so what the first thing we need to do is come up with the turn ratio. So I'm going to go N is equal to N2 over N1, which is equal to 100 over 10, which is equal to 10. So we have a turn ratio of 10. All right, so now let's go ahead and calculate what V2 is. So I'm going to say V2 is equal to N multiplied by V1, and that's going to be equal to 10 multiplied by 1, and so it's going to be 10 volts, okay, volts AC. All right, so that's good. And then finally, let's do I1. So then I2, and it's going to be, based on our equation, it's going to be I1 over the turn ratio. And so I'm going to I plug in 1 amp for I1, and then I have 10 for a turn ratio. And what I get is 0.1 amps or 100 milliamps. So what I've done in this is I have stepped up the voltage because I went from 1 to 10, and I have stepped down the current. And so let's do a final calculation here on power. So if I come over here and I want to say P1 is equal to IV, what I can do is I can just simply come in here and I can say, well, the current was 1 and the volts were 1, and so I ended up with 1 watt. Okay, so P1 is equal to 1 watt. All right, so let's go over here now, and we'll say, what is P2? Well, it's going to be I times V, and so now we're going to have, let's plug in I2 and V2. So what I have is, what was I? Well, it's 100 milli multiplied by 10, and if I put that in there, I got 0.1 times 10. Well, lo and behold, it's 1 watt. So I got P2 is equal to that. And look at what I got. P1 is equal to 1 watt, P2 is equal to 1 watt, but using this magnetically coupled system, or a transformer, I was able to step up and down the current and the voltage. Okay. Awesome. So the last thing that I'll say is the difference between an ideal and a non-ideal transformer. So, and we are talking about ideal transformers, okay? And that is where P1 is equal to P2. All right, there's no loss through the transformer, but there is non-ideal. There's always going to be loss in every system. And so what happens is that you are going to have some loss through the transformer. And what happens is that P2 will be less than P1. So you get some sort of loss in there. And all you do is you just have a loss coefficient that you apply to the power, and you basically don't get as much voltage and current out as you might have hoped. But it's just like every system. There's ideal and non-ideal. But this is an introductory class, right? So we're just learning about the introduction to transformers. So we always start with the ideal transformer and go from there. Okay, so that is it. That is the transformer and how it is used only on AC signals. Does not work on DC signals, but it allows us to step up and step down voltages and currents. All right, that's it, and see ya.